From goldbach density to Hardy-Littlewood correlations. Geometric interpolation through prime gaps and twin prime signals in normalized goldbach counts. Author Aaron Cattell. May 2026 draft. Abstract. Every even number greater than 2 can be written as the sum of two primes. This is the famous goldbach conjecture, still unproven after nearly 300 years. This paper does not prove it. Instead, it explores what the count of such prime pair representations reveals about the broader landscape of prime numbers. Starting from a prior spiral-based conjecture about prime locations, which was subsequently shown to be false in its original form, we identify two reformulations, called R3 and R4, that do survive mathematical scrutiny. R4 is a geometric result. The midpoint between the two primes in a goldbach pair sweeps linearly through a prime gap, like a clock hand. R3 is an analytic result. Fluctuations in the normalized count of goldbach pairs carry a statistical signal that points toward twin primes, consistent with Hardy-Littlewood theory. Computational experiments over 100,000 even integers confirm an AUC of 0.866 for twin prime prediction via goldbach density, and the R4 midpoint trajectory achieves a mean R squared of 0.973 for affine interpolation across prime gaps. 1. Introduction. The starting point of this program is a deceptively simple question. If an even number n can be split into two primes in many different ways, does the number of those ways tell us anything useful about where nearby primes are? An earlier conjecture, the goldbach spiral conjecture, proposed that the geometric centroid, average position, of goldbach pairs, when plotted on a prime spiral, lies unusually close to the next prime. Large-scale computation demonstrated that this global prediction fails for arbitrary even numbers. The original conjecture was therefore refuted. This paper asks, what survives the refutation? Two mathematically meaningful structures remain. R4, clock hand interpolation, the midpoint of the dominant goldbach pair sweeps geometrically through each prime gap. R3, singular series fluctuations, the normalized count of goldbach representations fluctuates in a way that encodes Hardy-Littlewood pair statistics. Central claim. R3 and R4 are not a new way to predict primes. They are geometric and statistical reflections of structure already known to number theorists, specifically the Hardy-Littlewood singular series and its relationship to twin primes. We are not claiming to find primes faster, or to prove Goldbacher's conjecture. We are saying, the way goldbach pair counts fluctuate is not random noise, it echoes a known pattern in prime pair density described by Hardy and Littlewood in 1923. 2. Definitions. We introduce the key objects used throughout the paper. Definition 1. Goldbach representation count. For an even integer n, define Gn equals number of pairs p, q, with p plus q equals n, where both p and q are prime. For example, G10 equals 2, since 10 equals 3 plus 7 equals 5 plus 5. Definition 2. Normalized goldbach density. Adjust the raw count by the expected number of prime pairs near n. Gn equals Gn times log squared n. This removes the overall growth trend, so we can study fluctuations. Definition 3. Prime gap. If P is the kth prime, the prime gap is G equals pp. For example, the gap after 11 is G equals 2, since the next prime is 13. Definition 4. Frontier pair regime. We say n is in the frontier symmetric regime when n equals 2p plus delta, with 0 less than or equal to delta less than or equal to g. In this window, the dominant goldbach pair is p plus delta, the pair whose smaller element is p, the largest prime not exceeding n is 2. Think of this as, we pick a large prime p, then let n slide from 2p up to p plus p. Throughout that slide, the pair anchored at p is the frontier pair. 3. The R4 clock hand theorem. Suppose the primes are embedded in a smooth geometric curve. Think of a spiral drawn in the plane, with each prime at a specific point on the curve. The theorem below describes how the midpoint of a goldbach pair moves through a prime gap. Theorem 1, clock hand midpoint interpolation. Let M delta denote the midpoint of the frontier goldbach pair when n equals 2p plus delta. Under the assumption that the embedding has bounded local curvature, i.e., the spiral does not bend sharply, we have M delta equals POS, p plus 2 times t plus o squared times, where t is the unit tangent direction at p and is the local curvature. Equivalently, the distance from M delta to the next prime p is dist M delta POS, p equals r times 1 or 2g plus o g squared times, where r is the distance from p to p in the embedding. Imagine a clock hand fixed at p. As delta increases from 0 to g, the midpoint M delta sweeps steadily from p toward p, like a clock hand rotating. The motion is essentially linear, straight line, with small errors proportional to how curved the embedding is. Proof sketch. The key step is a first-order Taylor expansion of the embedding. Because the curve is locally smooth, POS, p plus delta, almost equal to POS, p plus delta times t plus o squared times. The midpoint of the pair, p plus delta, is therefore M delta equals 1/2 times POS, p plus delta, almost equal to POS, p plus 2 times t. This is an affine, linear, interpolation along the tangent direction, hence clock hand motion. 2 exact corollaries. 2 special cases of Theorem 1 hold exactly, not just approximately. Corollary 1, start of gap. Delta equals 0 M, 0 equals POS, p, dist, M, 0, p equals r. When n equals 2p, the midpoint of the pair p is p itself. Corollary 2, end of gap. Delta equals gn equals p plus p dist, m, g, p equals r2. When n is the sum of 2 consecutive primes, the midpoint of that pair lies exactly halfway between them. 4. Numerical verification of R4. The theorem was tested on all even integers from 100 to 200,000, covering 17,984 prime gaps. Statistic. Value. Prime gaps tested 17,984. Mean R squared of affine, linear, fit 0.973. Median absolute error 0.041. Midpoints within 2 R of P 95.1%. Midpoints within 1 R of P 81.7%. Numerical conclusion. The affine approximation is extremely accurate. R squared equals 0.973. The small deviations are consistent with the curvature correction term O squared from the theorem and become smaller as the primes grow larger and the spiral flattens. 5. Hardy-Littlewood theory and the singular series. The analytic backbone of R3 is a famous result in prime pair counting. In 1923, Hardy and Littlewood conjectured Gn almost equal to 2c times n o log squared n times n, where c almost equal to 0.660168 is the twin prime constant. N is the singular series, a product over primes encoding local divisibility constraints. N equals pi underscore a pn, p greater than the singular series, n, measures how arithmetically convenient the number n is for prime pair representations. If n is divisible by many small primes, pairs p, q, with p plus q equals n are either more or less likely depending on the congruence structure. The product, n, captures this precisely. After normalizing, the asymptotic relationship becomes. This means the normalized goldbach density is, asymptotically, a scaled version of the Hardy-Littlewood singular series. From After normalizing, the asymptotic relationship becomes. This means the normalized goldbach density is, asymptotically, a scaled version of the Hardy-Littlewood singular series. The R3 twin prime signal. The singular series, n, takes larger values when n sits inside a twin prime gap, i.e., when the two primes surrounding n2 differ by 2. This is not a coincidence. It reflects that twin prime pairs generate unusually dense goldbach representations for nearby even numbers. Definition 5. Density residual. X_n equals g, n, 2c. This is the excess normalized goldbach density above the baseline twin prime constant. Definition 6. Twin prime indicator. T_n equals 1 if pp equals 2, else T_n equals 0. Observed covariance. Computational evidence shows. Cov X_n, T_n, 0. The density residual X_n tends to be larger precisely when the nearest prime gap is a twin prime gap. Using the Hardy-Littlewood approximation, X_n almost equal to 2c times n, 1, cov X_n, T_n, almost equal to 2c times cov n, T_n. In other words, when the goldbach count for n is unusually high, that's a signal, not a proof, that n is near a twin prime pair. The connection runs through the Hardy-Littlewood singular series, which is elevated near twin primes. Classifier performance. We tested how well X_n predicts twin primes across 100,000 even integers, using AUC area under the ROC curve, where 0.5 equals random guessing and 1.0 equals perfect prediction. Gap type. AUC, predictive power. Twin primes, gap equals 2. 0.866. Gap less than or equal to 4. 0.550. Gap less than or equal to 6. 0.517. Gap less than or equal to 8. 0.538. Gap less than or equal to 10. 0.505. Key finding. The signal is highly specific. AUC of 0.866 for twin primes, but near random for all other gap sizes. This confirms that the goldbach density residual is picking up exactly the twin prime enhancement encoded by the Hardy-Littlewood singular series, not a generic gap detection mechanism. 7. Interpretation and status of R1 R4. The original goldbach spiral program proposed 4 reformulations, R1 R4 after the global conjecture was refuted. Here we summarize what each means and what is now established. Claim. Description. R1. R1. Midpoint identity at n equals 2p. Exact tautology, trivially true by definition. R2. Perturbative proximity near n equals 2p. Finite scale effect, not a global law. R3. Normalized density correlates with twin primes. Supported by computation, reflects Hardy-Littlewood structure. R4. Clock hand midpoint interpolation through prime gap. Proven under smooth embedding. Confirmed numerically, R squared equals 0.973. The framework does not predict where the next prime is globally. It records how prime density fluctuates locally and how frontier geometry interpolates through individual prime gaps. 8. Future directions. The program raises 4 well-defined open problems. 8.1 Rigorous derivation of the covariance law. The positive covariance cov, x_n, t_n, 0 currently rests on numerical evidence and the Hardy-Littlewood heuristic. A rigorous proof would require replacing the probabilistic language with genuine asymptotic statements over finite intervals. Expressing twin prime events through truncated sieve weights. Studying the resulting bilinear correlation between goldbach density and twin prime indicators. A second approach uses the transference philosophy from the bounded gap literature, Maynard, Zhong, Polymath 8. Seek pseudorandom majorants for the prime indicator, then verify whether singular series fluctuations survive the structured or random decomposition. The strongest conceivable outcome would be an explicit asymptotic formula. Sigma_n less than or equal to x or g, n, 2c, times t_n kappa times x. For some positive constant kappa, though this is currently well beyond existing analytic technology. 8.2 Spiral-independent geometric formulations. The R4 theorem is currently stated in terms of a smooth spiral embedding. The geometric interpolation principle should hold independently of any particular embedding. A fully intrinsic version would express the clock hand law in purely metric or combinatorial language. Tangent flows on ordered prime embeddings. Discrete geodesic interpolation. One-dimensional transport along the prime index parameter. Local affine approximation in metric spaces. A key test: does the interpolation law survive under bi-Lipschitz transformations of the embedding? If so, the phenomenon should be regarded as intrinsic to the prime ordering rather than an artifact of spiral coordinates. 8.3 Sharper curvature error estimates. The current error term O squared is qualitative. A refined theorem would establish an explicit bound. M delta, L delta, less than or equal to c times squared times plus O cubed times. Where L delta is the affine interpolation path. If 1 could prove equals O, g to the power of 1, the interpolation law would become asymptotically exact over growing prime gaps. This would also allow classification of embeddings into regimes. Curvature regime. Behavior of M delta. High curvature. Nonlinear midpoint drift. Moderate curvature. Perturbative affine interpolation. Vanishing curvature. Asymptotically exact clock hand motion. 8.4 Connection to pair correlation observables. The deepest possible direction is a connection to mainstream analytic number theory via pair correlation statistics. Montgomery's pair correlation conjecture for zeta zeros studies the distribution of normalized spacings between zeros of the Riemann zeta function. An analogous program for goldbach densities would study sigma underscore n less than or equal to x of fn times fn plus h, where fn equals gn e.g. as a goldbach pair correlation observable. Formally substituting the Hardy-Littlewood heuristic, this becomes which connects to Ramanujan expansions, additive divisor correlations, and Seilberg sieve weights. A particularly ambitious objective would link goldbach density fluctuations to the pair correlation statistics of zeta zeros via the explicit formula, placing the program inside the broader circle of ideas connecting prime gaps, additive prime problems, and random matrix heuristics. Heuristics. 9. Conclusion. Summary. The Goldbach-Hardy-Littlewood program no longer seeks a global prime prediction mechanism. After the refutation of the original spiral conjecture, two meaningful structures survive. R4. A geometric interpolation law. The dominant Goldbach pair midpoint sweeps linearly through each prime gap, clock hand motion. R3. A statistical signal. Fluctuations in normalized Goldbach density are positively correlated with twin prime occurrence, consistent with the Hardy-Littlewood singular series. Neither result predicts where primes are. Both results are observational windows into local prime pair density and additive correlations, two phenomena that Hardy-Littlewood theory already knows about, now visible through the Goldbach count. The revised picture is modest but honest. Instead of a new theory of primes, we have found two well-defined, quantifiable ways in which Goldbach pair counts reflect the known structure of prime pairs. The next step is to understand whether this reflection is deep or superficial, i.e., whether R3 and R4 admit proofs independent of the Hardy-Littlewood heuristic. References: Hardy, G.H. and Littlewood, J.E. 19